am Dr. Rashid Ahmed from the Department of Physics of Kohat University of Science and Technology. In the subject of Mathematical Methods of Physics 2 with the course code PHY 222, we are at the lecture number 17 and the topic is Legendre's Equation. In today's lecture, I will explain to you the Legendre Equation and its solution. I will also give you its applications and different physical scenarios. So to begin with, the Legendre equation is a second order differential equation, as you can see over here. It has a constant L involved, but in the first term, as you can see, that it is a second derivative of y involved multiplied with 1 minus x square, a second variable, and in the second term then we have with a minus sign 2xy prime, so the first derivative of y prime, and in the last term we have L into L plus 1 into y is equal to 0. So you see that it is a second order linear differential equation, and what we want to do is to solve it. It has a very famous solutions called Legendre polynomials, but in today's lecture we will solve it with the help of a series expansion. And before we go towards its solution, I would like to mention its applications. It is actually used in spherical symmetry. In the problems where geometry is spherically symmetric, then we use them. We use this equation, and usually we write this equation in terms of spherical coordinates. But even if we don't write it in spherical coordinates, we can use it in a variety of physical problems. For example, these physical situations contain mechanics, so it arises in many problems in mechanics where we deal with the motion of objects. So we see that whenever the object's motion is a three-dimensional and it's having a spherical symmetry involved, so it could be very easily modeled with the help of a Legendre equation. Then we can have it in quantum mechanics, so it is very much applied in quantum mechanics, and it arises in many situations in quantum mechanics, so it has got uses over there. And then we can also use it, and it's applied in many parts of the electromagnetic theory, where we electromagnetic waves are modeled sometime with the help of Legendre equation. And finally in the heat. So you see that Legendre equation has got many applications in physics, ranging from mechanics, quantum mechanics, electromagnetic theory to heat, and therefore studying it and to be able to solve this equation is very important. So in today's lecture we will consider the solution by a series method. What do we mean by series method? Is that we will expand the solution in terms of the series. For example, let's start with this is our solution y, and in the Legendre equation you have seen that we had two variables y and x, so we expand y in terms of a power series. So the first term, as you can see, is a constant term having a coefficient a naught, and the second term is having a linear power x, linear power of variable x. So we have a1x, and the third term is actually the square of the x square. So we got a2x square, and then we have a3x cube and so on up to a and x. So you see that we have expanded the variable y into a power series in x. So once we do this, the next step is to calculate its first derivative. So because we will then use it in finding out our solution. So to I mean at the end the solution would be to calculate these coefficients you see over here from a0, a1 a2, a3, a4 to an. So we would like to calculate all these coefficients. So what we want to do now is to calculate the first derivative, and we with respect to x, that is y prime. So if we calculate the first derivative, that is y prime, and what we will get, the derivative of the first term will be 0 because no x is involved. So therefore it is a constant term with respect to x. Therefore its derivative will be equal to 0. So what we get will be a1, and a1 from this term. So a naught derivative is 0, but the second term will dx by dx will be equal to 1. So we will get a1 over here. So this term, actually derivative of this term is over here, and derivative of this term is actually 0. And derivative of this term, as you will apply the power rule, so it will be 2x. So 2x into a2. So derivative of this term is here, and similarly this will be with the cube, and derivative of this term is here, and so on. So we have calculated term by term the derivative of the whole series, and we got the complete another series which is actually the first derivative of this one. Similarly, we can have the second derivative, that is we want to now calculate up to second derivative, because in the Legendre equation you have seen that we had it's a second order linear differential equation. So we had y double prime as well. So we would like to calculate this derivative of this series up to y double prime. Now you would see in the second derivative, the derivative of this term over here will go to 0, but the derivative of this term will be 2a2. So the derivative is over here 2a2, and dx by dx is equal to 1. And similarly the derivative of this third term is this one, and the derivative of this term is this one, and so on up till derivative over here. So by this way you have seen that we have expanded a variable, a dependent variable in the Legendre equation into series, and then taken its derivative, and then taken again its another derivative. So after completing the differentiation with respect to x of this series, now is to go towards substituting these values. So what we will do now, that we will take this y prime and y double prime and put it back into the Legendre equation over here. So we will put it the y double prime value over here. So every term now will be multiplied with 1 minus x square. We will put the value of y prime over here. So every term of this y prime series will be multiplied with the minus 2x, and then we put y over here, and every term of the series will be multiplied with L into L plus 1. So by this way we will substitute term by term everything over here, and we will also then collect the different powers of x. The different powers of x we will collect. So so let's do this, and we have this table over here, where you can see in the column that we have the different types of terms, that is y double prime minus x square y double prime minus 2xy prime and L into L plus 1y, and this is the type of the term we are having. For example, we having a constant term, or we having a term involving x, or we having a term involving x square or x cube and up till xn. So let's understand that how this comes about. If you look at the first entry over here in this table, then we have 2a2. So if you go back, how we get this 2a2? So if you go back over here, and you see that y double prime, this first term over here is 2a2, which is a constant term. By constant we mean that no derivative, no x is involved. So you see that no x involved in these first terms. So this 2a2 and also y double prime. This is also a constant term, but it is associated with a y prime. And this is also a constant term, but it is associated with a y. So we are interested for our first entry in the table is 2a2 into y double prime, as you see over here, that this is constant and y double prime. But we want to look at the term which is constant but having coefficient minus x square y square. It is not in there, so this term is 0. Similarly, this term, that is minus 2xy prime, this term is also 0, its coefficient is also not there, but this term L into L plus 1 into y has this constant coefficient. So if you look back over here, so you will see that this L into L plus 1 term, because once we have put this everything in there in the Legendre equation, as by here you see in y we had a constant term a naught, so therefore this L into L plus 1 actually when we put a naught, so this gives us the constant coefficient, as you can see over here, a naught getting multiplied. So this is this coefficient is actually coming from the last term in y. So these were about the constant coefficients. Then you see that we have the coefficients for x as well and y prime. So you see that we have actually 4 types of terms over here. So we have 4 types of terms, and as you see, the y double prime, y double minus x square y double prime minus 2xy prime, and L into L plus 1 into y. And then all these 4 terms, all these 4 types of terms have some constants over here. So constant term or something which involves x. For example, let's see from where this term comes in. So we have y double prime 6a3. So if you look back over here, so this is 6a3 multiplied by x. So this term is actually 6a3 multiplied by x. So you should read it like x. So this x written in the row above here is actually multiplied over here. So this is in principle 6a3x. So this is 6a3x having a coefficient y double prime, and the coefficient of such type of term coming along with the x is 0, and coefficient of this term is minus 2a1, and coefficient of this term is L into L plus 1 a1. And again similarly you can continue this and can check the coefficient for the terms x square. You will find out that these are the coefficients, and similarly x cube, and you can extend it till reaching the power of xn. So you see that in xn we will have the coefficient for this term equal to that one, and similarly, so you see the last term is actually of type L into L plus y with a naught, a1, a2. You see all the coefficients coming over here, and here you also see this series looking like a series a1, a2, a3. Only the a naught is missing here. Here you see a naught, a1 both missing, and here in the first term you see the a naught, a1 is missing, but a2, a3 we have. From these collection of coefficients, different coefficients, after substituting the series for y prime and double y prime into the Legendre equation, we now have all the coefficients. So next what we do is set the total coefficient of each power equal to 0. By this I mean that if you look at the constant term, so we have 2 coefficients over here, that is 2a2 and L into L plus 1 a naught. So we have 2 coefficients over here. So what we do is we set this equal to 0. And why can we do this, and how we can do this? Because if you go back again to the Legendre equation over here, you see in the Legendre equation the sum of all the terms is equal to 0. That means that we can put the coefficients of each term, for example constants, separately, because they satisfy equation identically, which means that every coefficient can be put equal to 0 independently. So therefore we can put the coefficients over here, for example these constant coefficients equal to 0. So if we do that, if we put 2a2 plus this was the first coefficient, all others are 0, into L plus 1 is not equal to 0. So this equation now gives us a chance to calculate a2 in terms of a naught. So if you rearrange this equation, that is taking this to the right hand side and then calculating a2. So solving for a2, you will get the minus L into L plus 1 divided by 2 into a naught. So this is the value we got. And similarly, if we put the other coefficients equal to 0, for example of the power of x equal to 0, so this was the coefficient, and now if we solve it, so what would be the a3 here, and this goes up there. One more extra step we have also done in solving this equation, that we have factorized this L square L plus minus 2. So you see two factors, so that we can put it in this form. It will be later on, you will see helpful in obtaining the solutions and Legendre equations. So therefore we have factorized this already and put it into this form, that is L minus 1 into L plus 2 into 6. And similarly, if we put all other coefficients similarly like this, for example the third one, that will be 12a4 plus L square into L minus 6 into a2 is equal to 0, or a4 will be then minus, again we have seen that factorized L square plus L minus 6 over here into this form. So L minus 2 into L plus 3 divided by 12, and a2, but here you see that this a2 is appearing in this in definition of a4 we have a2, but we already have the value of a2. You can see over here that we have already a2 involved here. So what we can do now is to put this a2 into over here, a2 value of a2, and we get our final coefficient a4 in terms of a0. So by this way we have now even done this. So our purpose is now to generalize this procedure and get towards the general term of this series for A's, and to predict or somehow guess the general term. What we want to do is to calculate the coefficient, the last coefficient of a n plus 2. For this, if we put this coefficient equal to 0, and if we factorize this, if we factorize the second term over here, you can see that is L square minus n square plus L minus n. If you factorize this, you will get this one, that is L plus n, L minus n plus L minus n. So I hope you understand how to factorize this, and then again this can be put into this form, L minus n into L plus n plus 1. So here what we have done is to factorize the coefficient of the a n, and after the factorization we can now put this formula for general formula for the term a n plus 2. A n plus 2, as you can see over here, would be then equal to minus into L minus n, L plus n plus 1 into n plus 2 n plus 1, and a in terms of a n. So this is our general formula we have got for our n plus 2th term, n plus second term. This is our general formula, and it actually contains all other formulas. If we put the value of n is equal to, let's say, 0, then we will get a2. And if so, this will be a0. We know already what a0 is. If we put n is equal to 1, we will get a3 and a4 and so on. So all the coefficients we have derived or are actually contained inside this general term. Okay, so what our general solution now would look like is like going back to our solution. If you remember, y. And in this y, putting the values of all the coefficients, for example in a1, a2. So you see that everything turns out into this constant L. So in the first term it is independent of L, but in the second term we have this L, and all the terms are now contain the values of L, and we have actually removed these coefficients in terms of A's from here. And this is the second series. So we have got now two series, that is the a0 series and a1 series. A0 series, as you can see, is contains 1 and x square and x4, and so it is like a power, it is like a even series, where you get the power of x as even, that is x square, x4 and so on involved. And in the second A1 series, it's like an order series where you get the powers of x1, 3 and 5 and so on. So there are many interesting properties of these two series of this Legendre, and we can derive actually all the Legendre polynomials from here. And there are interesting properties associated with this Legendre equation solution, and we will see that whenever one of this series actually diverges for some values, the other one actually terminates for some terms. So we will see that one of them, if this diverges, then this will terminate, and this diverges, this will terminate. So one of them will terminate after few terms, and in this way we will be able to we will be able to solve our equation or to model our physical phenomena with the help of a Legendre equation. And these are some references you might want to see, and before end I would like now to summarize for you everything we have done here today for the Legendre equation. As I told you, Legendre equation is a second order linear differential equation, and it is useful in problems where spherical symmetry is involved. And we have its applications in mechanics, in quantum mechanics, in electromagnetism, and in heat. And today's lecture we have considered only its solution with the help of series. So what we have done is that we have expanded y in terms of power series, and then we have taken its derivative and second derivative term by term. And then what we done that the value of y double prime series and y prime series and y series we have substituted back into the Legendre equation and collected all the coefficients, and then term by term we put all these coefficients one by one equal to 0, because this had to satisfy the equation identically. We were able to calculate all the coefficients, and later on then we generalized the formula, and we got the general formula for a n plus 2 term. From this general formula then we were able to write the whole equation as a sum of two series. One is called A naught series and the other is called A1 series. I hope you have understood the idea of Legendre equation and its series solution. With this, I thank you all.